All right. Here we have 4.7. This is applied optimization problems. This is the calculus that all the calculus for business and calculus for social sciences and all those people, this is what they're doing. This is the kinds of problems they're dealing with. And this is where calculus in the real world is so powerful because you can take all of these different business functions or manufacturing things or biological processes, whatever you're talking about, and you can process them via calculus to find out where is a maximum value or a minimum value, whatever you're trying to aim for. And so we call these optimizations, but they might be minimization problems, they might be maximization problems, but in the end, very powerful. And these are pretty fun. So basically, the general setup is that you have it's a word problem. And so if you don't like word problems, then you might be a little caught flat-footed on that one. But generally, we have two things going on. We have something we're trying to optimize, whatever feature we're trying to optimize or minimize. And then we have some kind of a constraint. What's the limit? And what we have to do is put those two things together, and then we come up with our solution. So I'm just going to walk you through some examples here. They're pretty straightforward. There's just a ton of different ways to do this, but I think you'll find that the method for doing this is somewhat similar. So I'm going to give you the classic beginning optimization problem, which is this, that we have a wall and a gardener has a set amount of fencing and wants to make an enclosure, a rectangular garden, and fencing in three sides. So the wall will be one of the sides, and then using the fencing to make the other three sides. Given the fact that you only have so much fencing, what is the configuration that will get you the maximum area? So I think you can think about this in a ridiculous sense, that if I have and in this example we have 100 feet of fencing. So we can go all the way from, I'm going to make my fence 1 foot wide, my garden 1 foot wide and 98 feet long. That's ridiculous, but it is 100 feet of fencing. I can also go 1 foot wide in the other direction, and then 49 and a half feet the other way. Again, it's not practical. It doesn't make any sense. It's illogical. So the idea is, where do we get that exact spot where we can maximize the area? So in this case, what we have is, this is our constraint that we only have 100 feet of fencing. And what we want to maximize is the area. So we're going to figure out these two things via a picture or a diagram. So I've gone ahead and I've drawn a picture here for you. And I've labeled the width as X and the length as Y. So given that structure that I've made there, we can take these variables and plug them into both of these things. So in this case, if I want to talk about the area of this garden that I've just drawn, the area would be X times Y. That would be how you would figure it out. If I want to talk about the perimeter, which is the amount of fencing, it would be X plus Y. So 2x plus y, that would be the perimeter. So here's where we are. I have my area function, which is what I'm trying to maximize. I have my perimeter, which is my constraint component here. So now we need to put those together. So I can see that I have y's and x's. I'm going to go ahead and solve this equation for y and substitute in here. The idea is, I want to get to a single variable so that I can take the derivative of it, and we can optimize it. So I'm going to do that. I'm going to plug in this 100 minus 2x here, and now here is my area function. Then I'm going to take the derivative of that. So a prime, area prime. And I'm just like we did before, when is that value a min or a max? When is that slope equal to 0? So here's the function, 100 minus 4x equals 0, and we solve for x, and I get x equals 25. From this point, you need to be very careful about what the problem is actually asking you, because it might ask you, what are the dimensions? It might ask you, what is the actual area? So you may need to take this value and do some more things with it. So for example, this is simply the width. We just solve for the width. So if it says, hey, what are the dimensions? Well, it's 25 by, well, what? Well, if both of these are 25, then the missing side would be 50, right? 25 plus 25 is 50 via this equation. If I want to know what the area is, I would take that 25 and 50 and multiply them together, and I get 1250. So the actual, it's 1,250 square feet. That's the actual area. So be careful when you're looking at the problem for what is it actually asking. Let's look at a different example. The next classic one, this is a three-dimensional one. So in this case, this is a little tricky to visualize, but what we do is we have a flat piece of cardboard, a rectangular piece of cardboard. It's 24 inches by 36 inches. So if you can imagine this cardboard, and what we're trying to do is we're going to cut out some square pieces here on the corners, and then we're going to fold up these sides, 1, 2, 3, 4 sides, to make an open top box. Cut these out, fold those up, right, to make a box. So this is the base, and then these are the sides, right? So we want to, what's the maximum volume? Same thing. What's the constraint? What's the thing we're maximizing? I want to maximize volume. What is the volume formula? Well, it's length times width times height. The constraint formula comes from each of these, right? So we have to calculate what is the length, what is the width, what is the height. Well, the length of the original cardboard is 36 inches, but we've got to cut out these squares, right? And so I've just labeled them as X, right? But notice that I'm cutting out this corner and that corner. So the length of the box is actually this length right here. So that's 36 minus 2x, because this is x and that is x. Then the same thing on the width, 24 inches minus 2x's. And then what's the height of the box? Well, the height of the box, once you fold that side up, it's just going to be x. So here's my length, width, height. I'm literally going to multiply those all together. I did the work here. I'm not going to go through it with you, but you could certainly look there, and we get to here. X cubed, 4x cubed, here's minus 120x squared plus 864x. Take the derivative of that, I get this. Everything's divisible by 12, and it looks like I have a quadratic formula here. Plug that in your calculator or whatever you need to do, and I get 10 plus or minus 2 square root of 7, which is, so we get two answers here. So I want to look, first of all, at one answer right here. This bigger answer, if you look at the decimal value of this, it's 15.3 basically. But hang on. If the length of this was 15.3, right, if x was 15.3, look what happens here. The width is only 24. That means if you multiply this by 2, it's almost 30. So that answer is the ridiculous answer, right? It's that negative time answer we got when we're doing ballistic motion, whatever. It's a mathematically correct, but in the context of our problem, it doesn't make any sense. So we throw that out. So that answer doesn't make any sense. This is the correct answer, 10 minus 2 root 7, which is about 4.7. So you can plug that value in back into our length, width, height, and here is our approximations, which in this case are fine because we're just practicing this. And so if we multiply these all together, we get a volume of 1825 cubic inches. And here's the length, the width, and the height. We can do an example with revenue. So we can do lots of business examples for this, my friends. So in this case, we have a car rental example. And P is the price per day of the cars they're renting, and we have a range of $50 to $200 a day. And they want to know, well, what price do we set to maximize our revenue? And so then we can say, well, N cars, at however many cars are given by this formula. So 1,000 minus 5P. That's how many cars they can rent. So then in this case, you're just given this, and so then they say maximize revenue. And so part of this is, I have to know, how do I calculate revenue from this? Well, revenue, the amount of money they make, is the number of cars times how much do they charge per car. So number of cars times the price per car. So that's the revenue function. So in this case, We have what n is right here, right? So I can plug that in here, distribute that p, and then I have this, so I can find revenue prime, which is this, and so then we have the price is $100. Again, you may need to plug that back in here to find out how many cars is that. You may need to plug that back in here and here to figure out what's the revenue, how much money they're making a day. You get the point that you have to check the work. Same thing though. We have a problem, we have a constraint, and we find that that critical point. Last one here. This is a minimize one. So this is a minimum. So what we're doing is we're saying we need to make a box that has, again, an open top box that has a set volume. It has a volume of 216 cubic inches. But what is the minimum amount of cardboard that we can use to make that? I think you can see the application of this. Lots of businesses want to minimize their material use, and so this kind of problem is very very appropriate. The only thing here in the problem is we're kind of sneaky. It says it's a square base, so when we make our drawing, we have to be careful of that. So we have the volume, and the volume in this case it's a square base. So I went ahead and called one of the edges x. In this case, so x times x. This is a diagram of the base. Then we can call the height some other variable. I just used y. So then, in this case, using this, what I have here, the volume would be x squared times y, length times height times width. That has to equal 216. Surface area, which is what we're trying to minimize, that's going to be, because remember, there's 5 pieces to this open top box. There's the base right here, which is x squared, and then the 4 sides. Well, each side is x, y, right? So length times height. And so then we're going to say there's 4xy, so that's the 4 sides. So that's the surface area formula. Again, I can solve for y. And go ahead and plug that in over here, do some math, and I get this. I can go ahead, take my s prime and figure that out. And then here I get that x is 7.6, about 7.6, which means my y is about 3.7. And then you can figure out, what is the size of the base? What's the total surface? Whatever the question is. But same kind of idea there.